So this talk today I'm going to give is based on our work that we presented in Usenix Security Conference last month. It is joint work with my two advisors, Sal and Simha. And today we're really excited to talk to you about how we broke energy management, a fundamental component in all the systems that we have today. So this represents a new class of attack surface on systems, and we call this, this class of attacks CLKSCREW. So today, as we know it, energy management is indispensable. In fact, none of the systems that we have today can exist without energy management. So this is because, as shown by this chart over here, energy density is getting to a totally ridiculous point. So as we try to cram more and more functionality into the chips, we can create hotspots in them, so much so that if we don't manage the energy well, batteries will drain really quickly, and or worse, we may even burn a hole in our chips. So clearly, it's very important. Because it is so important, practitioners in the industry and researchers in the academia have gone to great lengths to optimize the way we manage energy consumption. So this is clearly very important. So in summary, we have these mechanisms, energy management, that we cannot live without and found on almost all the systems and is extremely complicated. So this is a perfect storm for security. And yet no studies have actually ever looked at this. And so in this work, we study the mechanisms and show that these systems can be fragile in terms of security. Our attack idea is this. Through software, we manipulate the energy management parameters to stretch the operational limits of the devices in a way that induces faults in security critical software. So why is this cool? This is because it allows us to sidestep all the requirements of traditional fault attacks, like needing physical proximity, separate equipments, and all the messy business. But more importantly, this opens up a very new attack surface on something very pervasive on the systems. And it also raises the possibility of doing fault attacks remotely. So in a nutshell, what have we achieved in this work? One, we found a new software-based attack vector that exploits the mechanisms that is very pervasive on the systems. And we show that this vector can be used to break the security guarantees of trusted execution environment, which happens to be the building block for many security critical applications like digital rights management and secure boot. We disclose our findings to the vendors, whose chips are going into hundreds of millions of devices out there. When we spoke to them, the vendors accepted our disclosure as highly critical and valid, and also very novel. And they're currently working towards mitigation and fixes. And finally, we hope that security can be duly considered during the future designs of the systems. So for the rest of the talk, we will first do a deep dive into a very widely used energy management technique. We will describe the hardware and software support for that, and how it provides the building blocks for the attack. And next, we would outline the challenges that we face and how we overcome them in the attack. And then we describe one of the attacks that we have in the paper, in our Usenix paper. And finally, we conclude with some thoughts and key takeaways. So recall that we want to stretch the energy management parameters beyond the operational limits of the device. So to do that, we exploit the existing software support for a technique called DVFS. It stands for dynamic voltage and frequency scaling. So first, let's investigate the underlying hardware regulators and that supports DVFS. There are two main factors that affect energy consumption. You have the operating frequency and the voltage. The higher the frequency of the voltage, the more energy consumed. So DVFS saves energy by turning these two knobs based on the runtime computing demands. You can think of it like putting a rubber band over both the knobs and carefully adjusting both at the same time. So of course, this sketches DVFS at a very high level, but in practice, how are frequency and voltage actually change on, say, a phone, for example? So this is possible due to a combination of hardware and software support for DVFS. At the hardware level, we have the circuit-level hardware regulators that control frequency and voltage. At the software level, we have the power governors that monitor runtime usage and initiate frequency and voltage changes using the device driver. By studying the source code of the device driver, we know that the software can control the hardware regulators via memory map registers. So this is really interesting because now we know that software can control some physical aspects of the underlying hardware. And so we focus our study on the regulators and their interfaces. For illustration, here we show the schematics of the frequency and voltage regulators. We reverse engineer from the Nexus 6 device. The important point to note here is on this schematics is that these regulators are configurable from software through the memory map registers. Now we know software can control frequency and voltage on the devices. A fair question to ask then is whether any limits are imposed on these configurations. What we have here is a Nexus 6 device advertised to run at 2.7 gigahertz. We measure the vendor recommended frequency and voltage at runtime. So the frequency we have is on the y-axis and the voltage is on the x-axis. After the measurement, we observe several discrete frequency and voltage operating points. So true enough, if you look at the top right-hand corner here, the highest frequency of 2.7 gigahertz is indeed as advertised. Now we will use the software interfaces that we described earlier to control the frequency and the voltage. For every voltage, we push the frequency upwards until we see some kind of instability. So this ranges from apps crashing, the device rebooting, or the device freezing. And we measure the frequency and voltage and plot the points here on the same figure. So here are the operating points based on our manipulation. As we can see from this graph, two things are apparent here. Number one, so there are indeed no safeguard limits in the hardware regulators. And number two, when we reduce the voltage, that also lowers the minimum frequency we need to see some kind of instability. So besides the Nexus 6, we also found similar behavior in other devices. So these are two of the devices that we tested out within our work. So now that we know that we can change the frequency and voltage with no limits at all, the next thing we want to assess is how dangerous this is on commodity devices. As we all know, ARM devices come with trust zone technology to isolate trusted execution environment to protect, say, your cryptographic keys or to enable like secure boot. So does DVFS operate across the security boundaries that are enforced by trust zone? Well, according to ARM, DVFS should not operate across security boundaries, well, in theory. So I'd like to draw your attention to two things. One, the recommendation is very, very recent, dated last year, August. And this is only based on the ARM v8M architecture. I cannot find something similar for the ARM v7 architecture. And according to the recommendation, any control registers that it can influence the clock, which can in turn affect the software running in the trust zone, they should only be accessible from the secure state. But all this is in theory. So what happens in practice? So this is a simplified view of a trust zone-enabled ARM core. Trust zone isolates the trusted code on the left from the trusted code on the right. And in our research, we found that the underlying regulators operate across the security boundaries. Both the trust zone code and the normal untrusted code share the same frequency and voltage regulators. When the untrusted code changes the frequency of the voltage, it affects the execution of the trusted code within trust zone. And now we know that we can affect the execution of the trust zone code from outside trust zone. So in some ways, maybe the vendors made this design decision to reduce the latency of the DVFS changes, because if you were to follow the ARM's recommendation, it means that all the DVFS will have to be done within trust zone. Now here's a quick look at how much latency each context switch from the non-secure world to the trust zone world would take. It actually doesn't seem too bad here. Perhaps as a form of defense, it may be necessary for us to consider to incur this cost to be a little bit more secure on the devices we have today. And now that we have explored the energy management mechanisms and their interfaces, we've uncovered several building blocks to an attack. In the next section, we will describe how we piece things together for an interesting attack. Ultimately, we want to ask, can we attack the trust zone code execution from outside trust zone using purely software-only control of the hardware regulators? The idea is to push the frequency and voltage past the operational limits of the devices to induce timing faults, and ultimately to break the confidentiality and the integrity guarantees of ARM trust zone. Note that we are not looking at availability here because it is trivial to break that over here. So before we talk about injecting faults, I want to give a quick sketch on why faults occur on the systems when you increase, say, your frequency past the recommended limits. Now, if you look at the devices we have today, all the digital circuits are made up of electronic components, and call them flip-flops here. Think of them as elements that store some kind of state, say 1 or 0. Each flip-flop has like an input and output. Because there are so many flip-flops here, they need to coordinate their operation with a common clock. The flip-flop can only change their state together at each clock pulse. And data needs to flow from one flip-flop to another, and usually there's some kind of intermediate path in between. Say we want to transfer a bit 1 from one end of the flip-flop to the next. It takes time to propagate this data bit. But more importantly, it needs to do it within the consecutive pulses of the clock signal. So there is a hard timing deadline in some sense. Say now we want to transfer the bit 0 to the other end. What happens when we increase the frequency too much? So this means that the clock pulses will come in really more frequency at any given time. Since the flip-flop changes its states only at the pulses, this also means that the data may have less time to propagate. And as a result, while the outputs is supposed to be 0, it remains as the old value 1. So at a high level, if you think about it, this fault actually results and exhibits itself as a bit flip from 0 to 1. For example, in practice, during our memory transfer operations in our experiments, we see faults like the following. Now that we understand like how faults are actually occur by manipulating frequency, let's talk about some of the challenges that we face to exploit this. To pull this off is very, very challenging to do it entirely from software. These are some of the challenges that we have to overcome. We will outline some of these challenges, and we briefly sketch how we address them. So for one, overclocking requires being able to set the frequency way past the suggested value, and especially doing it on a device which is, say, 2.7 gigahertz. And we have seen earlier that hardware regulators have no limits at all. So in fact, any operating points above the blue slope here is a possible candidate for attack values. And the next challenge that we have to address is that both the attack code and the victim code executes on the same device. So how do we prevent the attack code from attacking itself, or maybe the other non-victim code here? So we exploit the emerging trend that the energy management mechanisms are getting more fine-grained. In fact, many devices, such as the one that we attack here, have separate frequency regulators for each of the core. So we pin the thread execution of the attack and the victim code to different cores on the actual devices, and this helps to isolate the effects of the fault injection only to the victim thread that we want. And the environment that we're attacking is a very complex, is a complex OS. And to deal with that, we have to carefully design our attack to disable the interrupts during the window of attacks. And coupled with core pinning, this helps us reduce a lot of noise during our actual attack. And for many attack scenarios, we need precise timing as to when to actually deliver the injection of the fault, and for how long. We also need very fine-grained timing resolutions for the attack. For example, to give a sense of the difficulty, in one of the attack scenarios, we need to inject the fault within a very, very small window of about 65,000 clock cycle. And this actually happens within the entire victim thread that takes 1.1 billion clock cycle. So this is the kind of challenge that we have when we want to inject the fault in there. So for the timing resolution, we rely on assembly level no-op loops for high precision timing delays. And to guide the timing of our fault delivery, we rely on cache side channel based profiling techniques. With a general attack architecture here, we proceed to attack the two security guarantees of ARM trust zone. We explore two attacks in our work. So in the first attack, we break the confidentiality by inferring the secret AES key that is being stored within trust zone. Usually with trust zone over there, you shouldn't be able to grab or extract this kind of keys from outside trust zone. And in the second attack, we show how CLKSCREW can trick trust zone into loading a self-signed application. So in the interest of time, we will only describe the first attack. Please refer to our Usenix paper for more details on the second attack. So the threat model is this. We have an AES decryption app that is running within trust zone. It uses a secret key that cannot be accessed from the non-secure normal world. Now the attacker wants to extract this secret key out from the trust zone. and we assume that the attacker outside trust zone can repeatedly invoke the decryption app. And next, we assume that the attacker has software access to the hardware regulators and thus can inject the CLKSCREW fault during the decryption operation. And what we want to do in this attack is to induce a fault while the AES decryption is happening or running, executing within trust zone. So here we show an expected operation where we get the correct plain text from the decryption. Now we will re-invoke the decryption operation again, but this time we will induce a timing fault at the decryption operation to result in a faulty plain text. Now with this pair of correct and faulty plain text, we can apply the differential fault analysis from the Tansel's work to finally infer the secret key that we want. So to induce a timing fault to within the decryption execution, these are some of the parameters that we use for the attacks. The hardest part to this attack is actually to figure out how to inject a 1-byte fault to the 7th AES round during the actual decryption operation. So luckily, we can profile the execution environment of the trust zone code using hardware cycle counters, even when we are outside trust zone. This allows us to perform timing profiling of the victim app from outside trust zone. So the first question we ask is, how long does the decryption operation actually take? Does it actually vary from run to run? Because if it changes too much, we're going to have a tough time injecting the fault to where we want. So here we plot a histogram of the execution time of the decryption operation. And we see that more than 80% of the invocations take between 800 to 900,000 cycles. So in terms of execution time, there's not much variability in the thing that we want to try to attack here. And next, on the attacker side of things, recall that we're using the number of no-op loops to time the delivery of the fault. So is this an accurate proxy for controlling the timing of our fault attacks? So here we plot the number of no-op loops we use before the actual fault injection against the execution duration of the attack thread. So we see a clear, predictable linear relationship here. So this parameter that we're using actually offers a very, very good proxy for us to time and the delivery of the fault injection. So our differential fault analysis requires our fault model to achieve two things here. We need to exactly corrupt 1 byte within the 7th AES round, and next we will see how we can actually do that in a couple of slides later. So how likely are we able to inject the fault in exactly 1 AES round? Here we plot a frequency histogram of the number of AES round where the fault actually occurs. And we see that more than 60% of the resulting faults are precise enough to affect exactly 1 round of the AES. And how likely can we actually corrupt exactly just 1 byte, the ones that we want? So here we plot the frequency histogram of the number of corrupted bytes when we have 1 AES round that's being faulted. And here we see that out of the above faults that affect 1 round, more than half are actually transient enough to corrupt exactly 1 byte. We will end off with a summary of the results for this attack here. It is evident that controlling the no-op loops before the fault delivery allows us to precisely time the delivery of the fault to the targeted AES round. It takes roughly about 20 attempts to induce a 1 byte fault to the desired AES round that we want, and subsequently 12 minutes to conduct the fault, differential fault analysis to get roughly about 3,000 to 4,000 key hypothesis, and after which we could just brute force for the key that we want. And next, we want to round up the talks with some thoughts on the applicability of this on other platforms and possible defenses. So the industry is definitely trending towards finer grain and increasingly heterogeneous designs. So as a result, we're going to see designs which give software more control over energy management. We probably see this on the 64-bit ARM architecture, the newer Intel processors, and in fact, some of the cloud computing providers are even giving the VM guests more power and more control over the power management mechanisms. For thinking about all these security ramifications of these designs is certainly warranted here. And there are possible defenses, both on the hardware level and the software level, all across the different layers of the software, of the system stack. But one thing is clear when we are thinking about the possible defenses that we want. There is no clear defense that can entirely prevent the corkscrew style attack. So many of the design decisions that contribute to the possibility of this attack are in fact driven by very practical and pragmatic engineering concerns. So likely a full system response is needed for an effective defense. So to round up the talk, I'm going to briefly highlight the key takeaways from this work. We discovered a new class of attack surface, mainly enabled by the software interfaces of the energy management mechanisms. And we show that we can actually use that to attack trusted execution environment on devices, on an actual commodity device. So ultimately, this is not a hardware or software bug. It results from the fundamental design flaw of the energy management mechanisms we have on the systems. Such the future energy management designs should definitely take security into consideration, especially in the context of the use of hardware-enforced isolation. And with that, I'm going to end off at this slide, and I'm happy to take questions. Thank you.